This is part 4 of our revision series. So again, I'll give you some time to work on each problem and then we will discuss one by one. Okay, so few problems from elasticity. Okay, so take a look at this problem. I
If
know.
that just leaves one, then
See, it is a simple conceptual question. See, in the first case, what is happening? When you, let's say, hang a mass, there is a tension in the downward direction, which is equal to mg. And then because this wire is at rest, the ceiling is also applying a tension in the upward direction. So you have two forces pulling the string from either ends. Now, if you take the second case also, I mean, I know it's going over the pulley, but if you think about it, on either side you have mg
yeah,
tension. The other side is also mg, right? Now, in both cases, as far as the stretching goes, the string is getting pulled almost like with the same forces from either ends. So then the elongation should be same.
yeah.
Understand? So the answer is B. So keep this in mind. Okay, so take a look at this problem. So 0.1 is correct. The stretching of any wire, you can say that it is like stretching a spring. Okay, so when you stretch a spring by an amount x, the potential energy stored is half kx square. Okay, so that's the potential energy stored. So if you look at it, I can actually write it as kx into, let's say, x by 2, or maybe I'll say initially there was no stretch, now you have a stretch x and then by 2. So we're taking force and then multiplying by the average extension. Okay, so x by 2. So we can do the same thing here. The force is 200 newtons and the extension is 1 millimeter, so which is 10 to the power minus 3, and then divide by 2. So you will get 0.1 joules. Very nice. Now take a look at this problem. Here, if you have a massless wire and then a block is attached at the lower end, I can use the definition of Young's modulus, which is force by area, which is mg by A, stress by strain, so delta L by L. So this is mg by AY. Now you would have used this directly, but for this to be correct, the wire needs to be massless. Okay. Now in our case, the wire has mass. Moreover, we are not attaching anything at the bottom. Okay, so it is getting elongated because of its own weight. Okay, so if I take the wire, so let's say I'll give some thickness because it has mass, let's say, just to think about it. Okay. Now, what you have done is when you, let's say, substituted the mass density into volume, you got, I think we forgot L right here. Yeah, there will be L. So you get rho, area disappears, and then rho L square G by Y. But think about this for a moment. Each section of the wire elongates because of the tension that gets applied on either end. So if you take any section here, okay, so if I pick a section here, the tension here and then the tension above. Okay, so these two tensions there, because of the internal forces, the restoring forces will try to bring the section back to the original shape when these forces are, let's say, gone. Okay, so each section is getting stretched because of the pull happening on either of the ends. Now, when you have a massless wire, if you take any section, the tension everywhere will be same, and then that is equal to mg. But here, that is not the case. Okay, so if I take the lower portion of the wire, uh, the earth is hardly applying any force. So that means if I take the lower sections of the wire, the force is lower. If you, as you go higher, if you take the upper section, it is actually bearing the weight of the rest of the wire. So that means the tension in the upper sections is higher. So as you go up, the tension increases. Okay, but uh, if you think about it, if I take any section, let's say if I take a section of length y, the tension here would be equal to weight of this wire. Okay, so if the total mass is m, so I can get that by m by L into y. So the tension is varying linearly. You understand? If the tension is varying linearly, you can actually work with average. So you don't have,
Average.
yeah. I mean, when you don't have any weight, then there is no extension. When you have weight, you have some extension. So instead of taking this as the extension, you can take half of that extension. You're basically taking some sort of average. So the answer will be divided by 2. Okay, so if you don't want to, let's say, use calculus. So right now that is okay. Okay, so what we are really trying to do is, we are imagining that this system is like a massless wire, but instead of, let's say, having mass m, you can actually attach a block of half the weight, or let's say half the mass. Okay, and then this massless wire will have this elongation. Okay, instead of mgl by ay, you will get mg by 2 ay into L. You understand this idea? Okay. Now, suppose if you want to understand why this is even true. Okay, so if you look at the wire, so we are going with the definition. Okay, so the extension is the tension into L by A Y. Is it okay?
Mm.
Now, if I take this wire, if I take a section, a small section here, so this is my sample section. The tension in that sample section is because of the weight of this lower part. Okay, so if this lower part has length y, okay, earth is applying a force. Okay, so of how much? It will be m by L into y into g. So the tension here would be equal to this. You understand? So that is the tension stretching that sample section on either end. Okay, so the tension here will slightly increase, but I think because we are taking a small section of length dy, we can say that on either end the tension is same. Okay, so are you with me so far?
Yeah, yeah.
Okay. Now for the sample section, we can say the extension is, let's say, ds, suppose. Okay. Now the tension would be m g y by L. Now that sample section is a tiny piece of length dy. So the length happens to be dy there. And then you have A and then Young's modulus y. So if you want the total extension, you just have to integrate. So the total elongation will be, let's say S is the total elongation, you'll have to integrate this ds. So I have mg by L-A-Y and then integral y dy. We're going to integrate from 0 to L. So you will get mg L square by 2. I think A disappears, so 2y. So you understand this is what, oh, sorry, in this case, A doesn't disappear. When I have density into volume, I think A disappears.
Mm.
You understand the idea here?
Yeah.
Okay, so try this problem. Okay, so that's the right answer, 9F. Okay, so we can just use the definition. Young's modulus is same because we are looking at the same material. So Young's modulus is force by area into delta L, in this case delta X by L. Okay, so maybe that's the first wire. Now for the second wire, Young's modulus will be same. Okay, so we want to try and find the force required. Okay, if the volume is same, if the area of cross section is 3 times, okay, so what would be the length? Length would be 1/3, right? So that's L by 3, and the area is like 3A delta X. So from here, if you see, I think we get F2 and then L by 9A into delta X. So I think if you compare these two, you should get F2 as 9F. So B is correct. Very nice. Okay, so few problems from fluids. Okay, so take a look at this problem. Okay, so in this problem, you have a container, water is filled up to a height of 2 meters, and then the container is given an acceleration a to the right. So if at this point the pressure equals the atmospheric pressure, we need to find the value of this acceleration a. Now what that really means is the water will take this shape, right? Okay, now if you have ever looked at the water level in a water bottle, when you tilt it, the surface is always horizontal. Okay, so that means the water surface is perpendicular to the net force acting on the water particles. Okay, so now because the surface is inclined, that means if I pick any water particle, the net force, let's say mass of that water particle is m, suppose. The net force should be perpendicular to that. So keep this in mind. Okay. Now we are trying to analyze this from the frame of the container. Okay, so here you will have a pseudo force. So this is the net force. What other forces are there? So there is a pseudo force acting in the opposite direction of the acceleration, which will be ma, and then mg is acting downwards. Okay, so that's how these forces will be aligned. Okay. Now, if I look at this angle theta, so I don't know, let's call this height as h. We can anyway figure this out. If this angle is theta, you can see from geometry, so this angle is also theta, right? So we can say that tan theta is, you can write it in two ways, tan theta. So I can write tan theta as, if I'm using forces, I can write ma by mg. Okay, so if I'm using height and let's say length of the base, I can use h by 3. Okay. So we get a by g is h by 3. Now I need to find h. That is easy. I think into the board, the width of the container is same. So if I'm looking at the volume is same. There is no spillage here. So the volume initially and then right now the volume is same. So what is the volume of liquid initially? the base area is 3 into 1 and the height is 2. Okay, now the I'll have to take the cross section. Okay, so the cross section is a triangle. So I'll take half h into 3 and then into the board width is 1. So from here, I think h is 4 meters. Is it okay? So if h is 4, I can write 4 by 3. So A will be 4 by 3 G. Are you okay with this?
Yeah.
Now take a look at this problem.
Like you discussed.
No, one thing is, whenever you have a large tank and then you have a hole on the side wall of the tank, you just remember that the speed at least is just the speed attained by any freely falling object.
Oh.
Yeah. So in that case, what is the answer?
Root GH.
Yes.
2GH.
So keep that in mind. So that way you can just answer this is D. But otherwise, here to get that, we're supposed to use the Bernoulli's equation. Okay, so let's say you have this large tank, and then you put a hole, and then we are asked to find the velocity here. Now, I take this point as 2 location, and then this location as 1. What does Bernoulli's equation say? The pressure energy, P1, plus rho G H1 plus half rho V square. Okay, it's saying that the energy is conserved, right? Is equal to P2 plus rho G H2 plus half rho V2 square. Now, the top surface of the liquid is exposed to atmosphere, so P1 is P naught. And the right hand side, P2 is also P naught because at the hole here, it is also exposed to atmosphere. Now, the location of the hole we are taking as a reference point where the potential energy is 0. So this is potential energy per unit volume. Okay. So we will say, okay, point 1 is at a height h. So there is potential energy. So rho G H we will write. And then understand this, whenever you have this word large tank, or sometimes in these exams, they don't even mention, they just say tank. Okay. Assume that the area of cross section is very large. So in that case, the velocity with which the surface goes down, the speed with the surface goes down is almost like 0, negligible. So when you take half rho V square, I can just take it as 0. Then the right hand side rho G H2, that will be 0 because I have taken that as the reference location. Plus I need this speed, let's say half rho V square. So if you look at this, you get V as square root of 2GH. So that is how you actually get it. But I think you can also like keep this in mind. If I drop a stone here, initial velocity is 0. By the time it reaches that hole, it will have the same speed.
Okay.
I think the Torricelli was the person who observed this for the first time. So this is also called Torricelli's law, by the way. Okay. Okay, so take a look at this one. Yes, that is correct. Okay, so here what we can do is we can use the previous result. So suppose I'm looking at the water in the tank when the height is h, suppose. Okay, so the velocity with which the water comes out is square root of 2gh. So at this location, at the surface of the water and the hole, I can use equation of continuity. The rate at which the surface level is going down, which I can write it as the volume of water going down, I can write it as A into velocity, which is dH by dt. Because it is going down, I'll have to use a minus sign because dH by dt is negative. And at the hole, whatever volume is going down at the surface level, is the same amount of, let's say it's the same volume that is getting out of the hole. So we can say that is A V. So here you can write minus A into dH by dt is A into square root of 2gh. Now you just separate the variables. So what do I have? Let's say I'll, and then you integrate. Okay, so at t equal to 0, the height of water is h, and then at some time t, the height of water is h by 4. This is a simple integral, minus a by a. You know this 2 into square root of h, right? And then you have h by 4 and h. The right hand side has root 2g, sorry, square root of 2g into t. Now the left hand side, when I substitute, I think you'll get root h by 2 minus root h, so which is root h by 2. So left hand side I have a by a into, you'll get just root h. In the right hand side you have root 2gh, sorry, why am I saying root 2gh? Square root of 2g into t. So t would be, yes, B is the answer. Okay, so take a look at this question. See, one simple and quick way to keep this in mind is when you have this capillary rise. Okay, why does liquid rise in, let's say, tubes of very small area of cross section? The surface forces are dragging the liquid up. Okay, and then they're dragging. They cannot drag forever, right? Because the liquid, there is gravitational force acting on the liquid also. So the surface forces are acting against the gravitational force. Okay, now in a freely falling elevator, it's a weightless situation. So that means only surface forces are sort of effective. Okay, so then the surface forces will try to drag the liquid all the way to the top of the capillary tube. Okay, so the answer will be 20. So keep that in mind. Yeah. Okay. So how about this problem? So in this problem, you have a solid ball falling through a liquid of density rho 2. And then we're asked to find the terminal speed. The viscous force is also given. Now, the terminal speed, by terminal speed, I think you understand that the speed is not going to increase thereafter. So the acceleration is 0. So the net force basically is 0. So if you look at the spherical ball, if it is moving with this terminal speed, let's say Vt, the net force on it is 0. So the gravitational force acts in the downward direction, which is mg, which I can write it as mass is rho into volume into g. Now the buoyant force acts in the upward direction. The liquid has density rho 2. So the buoyant force is rho 2 into volume into g. Now, in addition to these two forces, you also have this viscous force, which acts in the opposite direction of the velocity, which is given as kv squared. So we'll write it as kvt squared. Because the net force is 0, I can say kvt squared plus rho 2 v, sorry, this is rho 2. Oh, what did I erase? What I wanted to erase, I did not erase that. Funny. Okay. So this is rho 2 Vg is equal to rho 1 Vg. So Vt will be, I think, Vg into rho 1 minus rho 2. I think you're right. Okay, so B should be the answer. Okay, so you like this topic, simple harmonic motion? Yeah, students love this topic. Okay, today we will do only few problems. Okay, so later on we will see. Okay, so take a look at this problem. Very good. So that is correct. If you look at the time periods, I think they will get in phase again at the starting mean position. Okay, so if that is what is going to happen, at the mean position, the velocity is maximum, which is a omega. Okay, so the amplitude is same. Did they say the amplitude is same?
They don't.
Huh?
They don't say amplitude is same.
Okay. The time periods are given. Okay, I think the amplitudes are not given. I think it is not correct actually. You need to have amplitude same. So let us assume amplitude is same. Okay, otherwise, because the speed depends on the amplitude. Okay, so the maximum speed is a omega. Okay, so amplitude, let's assume amplitude is same. Okay, so now for the first particle P, A into omega is 2 pi by time period, which is 3 seconds. And then for the other particle Q, it is A into 2 pi by 6. So that is how we actually get 2:1. If the amplitudes are different, I can't answer this actually. I think let us assume that. Okay, so try this problem. Whenever they ask you time related questions in SHM, the good thing, well, it's a good thing. What you should do is you should map your SHM to uniform circular motion. Okay, and then it becomes easy. So why? If you take a particle moving along a circle with constant speed, suppose. Okay, so let's say the center is at the origin. So if there is a particle moving with some angular velocity. Now, if I imagine that the particle is opaque, okay, so the light does not pass through the particle. If I shine light from above, and then if I have a screen here, okay, so if this is a screen, so you can see that the shadow of the particle, let's say if this is a ball, the shadow of the particle will oscillate. Okay, as the ball goes around the circle, the shadow oscillates between these ends. You understand this?
Yeah.
Yeah. So if A is the radius of the circle, then the amplitude of oscillation for the shadow is A. Right. So we can actually go from SHM to uniform circular motion to answer questions. So here the amplitude is given as 5A. So what we can say is, okay, so if I have a particle, this is the mean position along x-axis. So right extreme is 5A and the left extreme is minus 5A. Now the particle is here at position 4A plus 4A. And then we want minimum time to go from 4A to 3A. So it is going straight from here till here. Let's say this is 3A minus 3A. So now if I map it back to the uniform circular motion. So what I can do is I can imagine that the circle radius is 5A. The particle is right here, okay, which is mapping with this. Okay, so this will be 4A. And then if I imagine a vector joining the particle and the center of the circle, that vector rotates and then moves to some position here, let's say this position, which maps with 3a. Okay, so this is 3a. Do you understand this?
Mm.
So now, if I map it to circular motion, I can say the angle turned will be omega into time taken, right?
Mm.
Now, all I have to find is this angle. Now, you know this famous triangle. If this is 4a, 5a, this is 3a.
Mm.
3, 4, 5 is 37 degrees. And this will be 53 degrees. So that means in this problem, to go from plus 4a to minus 3a, the angle turned is 90 degrees. Okay, so theta is pi by 2. And then omega, we know 2 pi by time period into t. So the required time is t by
3/4.
So the answer is 2. So whenever they ask you time related questions, go back from SHM to UCM and then just use that theta is equal to omega t. It's much easier. You're okay with this?
Yeah.
Okay, so take a look at this problem. So that's the correct answer. So in this case, it is as good as our simple spring and block system. Okay. Now, whenever you have vertical spring and block systems, keep this in mind. You can ignore the forces in the equilibrium position. So, okay, so forces in the equilibrium position can be ignored. Because they don't take part in oscillations anyway. So they are always there. Okay, so forces in equilibrium position can be ignored. So keep this in mind. Okay, now right now the spring is anyway stretched. So if I, let's say, stretch it further by an amount, let's say x, then the spring force increases by kx. So that extra tension is providing the restoring force. So you would just write minus kx is equal to mass into acceleration of the block. So if you look at this equation, it's almost like our basic spring block system. So the answer should be A, 2 pi under root m by k. Very good. Okay, so how about here? Try to look at this problem. Again, that idea, you can ignore the forces in the equilibrium position. So the spring is already stretched. So that amount of stretch, we don't have to worry. So here, if you look at it, let's say if I displace the block down by an amount x. Okay, now you'll have to worry about constraints a little bit. Imagine if I hold this pulley and then drag it down by stretching the spring, if I pull it down by 1 centimeter, okay, if the pulley is moved down by 1 centimeter, the string here 1 centimeter will be loose and 1 centimeter will be loose. So you have 2 centimeters available to take this block in the downward direction. So the block can be taken down by 2 centimeters. You understand it? Okay, so that means when I stretch the spring by an amount, let's say 1 centimeter, I can actually take the block down by 2 centimeters. You understand? So if I am only taking the block by an amount x, the spring needs to be stretched by only x by 2. That is the first thing that you need to understand. You're okay?
Okay. Yeah.
So now here the additional spring force. Okay, so we in these cases we work with additional forces. Better give me a minute. Huh? Okay, so we have to work with only additional forces. Okay, so that is good enough. So the spring will provide an additional force of k, additional stretch is x by 2, so kx by 2. So that is the tension here. And then we know if I look at the free body diagram of the pulley, on either side of the pulley, the string will bear this force kx by 2. So that means the additional tension in that string will be half of this. So that would be kx by 4. So when you write down the Newton's second law, you're writing k by 4 x is equal to m into d2x by dt square. Now instead of k, you have k by 4. So instead of k, you will have k by 4. So the answer will be B. You understand this?
Okay, yeah.
Are you hearing a lot of drilling noise and then
No.
you're not hearing? Huh? You're able to just hear my voice.
Yeah.
Oh, this mic is nice. Okay, it is cutting down that background noise. Good. Okay, so try answering this question. Okay, so here, if I allow the block to go down by an amount x from the equilibrium position, okay. Now the pulley has to go down by an amount x. So that means I need x length here, x length here. But on the left hand side, I have a string. So I cannot get x length from the left hand side. Okay, I can only get the extra length by stretching the spring alone. So that means the spring gets stretched by what amount?
2x.
2x. Very good. Stretched by 2x. So the additional force that the spring applies is k into 2x. Now, if I look at the free body diagram of the pulley, 2x, k into 2x here, the tension in this string is also k into 2x. So this string will apply an additional tension of twice of k into 2x. So that is k into 4x, you can say, or 4kx. So now 4kx is the restoring force. So we can write, let's say the equation as minus 4kx, or you can just say that you have a spring block system where the spring constant instead of k, you have 4k. So what will be the answer now? It will be
C.
Yeah. Okay. You understand this? Okay. Now take a look at this problem. Okay. So here, let us not get into too much of detailing, but if you look at it, the strings are connected linearly. Okay, geometrically it appears parallel, but they're connected, right? So they're actually in series. Okay, so whenever you have springs in series, let's say K1 and K2, you can replace them with a spring with spring constant K1, K2 by K1 plus K2. I think this you know. So that means it will be K1, K2. So I can replace it with a spring having 3K by 4. So let's say I call that K prime. But my system will become like this. So you have to be careful. When I replace, I'm having a single spring like this with the K prime. Okay, now if you look at the previous problem is exactly like this. So what
Yeah.
was the answer? 2 pi square root of m by 4k or 4k prime, you can say. M by 4k prime. Now I put that k prime here. M by 4 into 3k by 4. So this 4 disappears and then we'll get answer as this. You understand this? Again, we can analyze this further and understand why I should take it as k1, k2 by k1 plus k2. But I think keep this in mind. If you have two springs in parallel, you can just add the force constant, replace with a single spring.
Okay.
Are you okay?
Yeah.
Okay. So few problems from gravitation. Okay. So try looking at this problem. So it is mv square actually. So here I think, I know, I think this problem somehow ignores the satellite. Let's say if we ignore, suppose, satellite. So I have, let's say Earth has mass m, and the particle, when it was with the satellite, so it has that velocity of the satellite. Okay, so v. Now, if r is the radius of the orbit, the energy here is potential energy, which is minus g mm by r plus kinetic energy half mv square. Now you are changing the kinetic energy, okay, so of that particle, but this potential energy will be there. Okay, so this potential energy plus kinetic energy. Okay, so that gives you the total energy. Now the potential energy will be there. Okay, now suppose if I give particle v prime velocity, so the kinetic energy will become half mv prime square, but the potential energy will still be there, minus g mm by r, when it was, let's say, projected at the time of ejection. Now, when it goes to a far off place where it escapes from the gravitational field, the total energy, instead of being some negative value E, it will be zero. So half mv square. So from here, you can see that, oh, sorry, I should write half mv prime square. That's the kinetic energy. So half mv prime square will be g mm by r itself. Now, how do I get this GMM by R? I can use the concept of centripetal force. The centripetal force is provided by the gravitational force. So GMM by R square is equal to mv square over R, right? Now, GMM by R would be, from here, GMM by R would be mv square. So that means this is mv square. Okay, so very good. So that is correct. Okay, so try this problem. Here, I mean, if you want to take a guess, actually you can take a guess. Because the potential has to be obtained by integration.
Yeah.
So you can say it will be like complicated, slightly complicated answer. But gravitational, when the object is in a gravitational field, unit mass, if you want to take it away, you have to do positive work. The external force has to do, literally do positive work. So the negative answer cannot be there. And then mostly I'll take a guess from between the D and A. Maybe I'll go with A. Okay. You understand? So you can take a guess like that, but conceptually, what is happening here? If I calculate the potential at P, okay, because they're talking about unit mass, the work done should be the absolute value of the potential. That's it. Okay, so in this case, whatever potential you have, that's the potential energy, because you have unit mass. You're taking unit mass to infinity. So I basically have to calculate potential. So if I take a ring here, so imagine out of this, I'll take a small ring. Let's say there's a ring of radius r, suppose. So the radius r, and then thickness is, let's say, dr. Okay, so I'll take a ring of radius r, thickness dr. Now every particle in that ring is at the same distance from P. Okay, so which we can calculate. So the potential due to the particles in that ring would be, let's say I'll write dv as, it will be minus g mass of that ring. So how do I get the mass of that ring? So let's say I'll use some mass per unit area as sigma. Okay, so I'll get sigma into area would be 2 pi r dr, that ring area. Okay, now that is mass, and then I divide by this distance. Okay, so this distance, so that would be square root of r square plus 4r square, which will be 16r square. You're okay?
Okay.
Yeah. Okay, so this plus this. Now, to get the potential, I'll have to integrate this. Now, to do the integral, what you can do is, let's pull the constants out. G sigma pi, just let that 2r dr stay inside. So I have 2r dr by square root of r square plus 16r square. Now you know this method of substitution, right, in integrals. So if I take whatever is there inside the square root, let's say r square plus 16r square as u, I'll get 2r dr as du. So this will become integral u by square root of u, du by square root of u, which is 2 into square root of u. Okay, so the integral will be minus g sigma pi multiplied by 2 into square root of r square plus 16 r square. And then now you substitute the values. So you're going from 3r to 4r. Okay, so when I substitute 4r, what do I get? 16, so that would be 32. Okay, square root of 32 will be what?
But then when you substitute, it will become 16 into 16. No?
16 plus 16, right? 16 square, 16r square plus 16r square.
Oh, okay. Yeah,
32. So square root of 32 is 4 root 2. So that means you can continue from here, but I think you can just pick the answer A, because the other place you will not get 4. Negative cannot be the answer. And then if I substitute 3r square, that's 5. We are getting that 5. Okay. Yeah. Okay. Try this problem. I think that is the correct answer. So I think we can find the position where the gravitational field is 0. So let's say 4m. So let's say this is the position. I think this will be closer, yeah, farther from 4m. So let's say x, mass m will provide a gravitational field of gm by, sorry, we'll take g small m. So imagine that is small m by x square. And then the other guy will provide g into 4m by r minus x whole square. So 1 over x is equal to plus or minus 2 by r minus x. Okay, so r minus x will be plus or minus 2x. I think minus x doesn't make sense. So we'll have x is r by 3. So then once you have x r by 3, the potential will be minus g m by r by 3 whole square. Sorry, not whole square, just this much. And then minus g into 4m by, so the other distance will be 2r by 3. Okay, so what do we get here? I think, yeah. So what are we getting actually? So 3, and then this will be, yeah, so 6, yeah, minus gm by r. Yeah, D is correct. Okay, so try working on this problem. See, what is the problem saying? If one second, what happened? See, if this is the Earth, and then you have a satellite, let's say that particle is the satellite, and then you have to give some energy. So that is the kinetic energy that you're giving. Okay, so on the surface of the Earth, you have kinetic energy, you anyway have potential energy, which is minus G capital M by R. Now, if it has to be, let's say, launched into an orbit of radius 2r. Okay, so I think my diagram is completely out of scale. Okay, but when it is in this orbit, let's say it will have velocity v, suppose. Now, how do I get that velocity? I can get that velocity by using the fact that the gravitational force, which is G by R square, which is 2R whole square, is providing the necessary centripetal force, which is mv square by 2R. Okay, so 2R is the radius. So we get half mv square, the kinetic energy there, as G capital M by 4R. So that is the kinetic energy there. So now I'll write the kinetic energy when the satellite is in the orbit. So G capital M by 4R plus the potential energy. So what is the potential energy? Minus G by the distance is 2R now from the center of the Earth to the satellite. Okay. So we get this here now. So I think G by R is common everywhere. So I sent this to the right hand side. I have 1 plus 1 by 4 minus half. So how much is that? So 4 plus 1 and then minus 2. So what are we getting here?
3
Okay.
by 4.
Yeah, 3 by 4, right? Okay, so 3 by 4 G by R. So but 3 by 4 is there? I think we would have made a mistake here. Just check. Okay, so I found the mistake. What are the problem? We did not read it carefully, so I think we'll have to read it carefully. See, they're saying altitude of 2R. So that
So it will be 3R.
This should be 3R. So all these places, they should be 3R. So I think, yeah, we will have to change this. So even this will change, right? And then this entire thing will change. We have to read carefully. Yeah, paying attention is everything actually. You understand, beta? So even I'm teaching, I'm making so many mistakes. So this will be 3R and this is 3R. So half mv square will be how much? Mv square over R will be G by 3R. So I think, what is half mv square? It will be, I think 6R, Jm by 6R. Mv square will be Gmm by, I think I'll write here, Mv square will be Gmm by 3R. So half mv square will be this. So here we are supposed to put Gmm by 6R. So the, and then this will be again
3R.
3R. So how much do we get here? So this is minus Gmm by 6R, right? So K will be, yeah, 5 Gmm by 6R.
6, yeah, okay.
Yeah. So you have to be careful sometimes. Okay, beta.